Alright. So we'll venture into the new form of trigonometry. You would have to unlearn a few things that you learned till your class 10 about trigonometry, and we'll give a new look to trigonometry, give it a generalized appearance. You would have to break loose from the fact that has been imposed upon you, terribly imposed upon you, about trigonometry being about trigonometry confined to a right angled triangle. We would look at the trigonometric ratios in a very general manner. Very general manner. Now, this is the Cartesian plane, the XY plane. And you know, different points on these planes are located by different pairs of numbers, x, y. An ordered pair x, y would locate different points in the plane. Now, imagine a rotating line. Imagine a rotating line. Let's say this is a rotating line OP, whose length is R. Imagine a rotating line OP whose length is R. And with this rotating line, we are going to associate an angle theta. We are going to associate an angle theta with this rotating line. If the line has rotated in the anti-clockwise sense with respect to the positive direction of the x-axis, look, this angle theta will always be measured with respect to the positive direction of the x-axis. This is the positive direction of the x-axis. Henceforth, this would be our reference line for measurement of angles, towards measurement of angles. When the line rotates in an anti-clockwise sense with respect to the positive direction of the x-axis, we deem the angle theta as positive. In contrast, when it rotates in the clockwise sense with respect to the positive direction of the x-axis, we refer to that angle as negative. For example, suppose this is the position of the rotating line, and let's say this angle is 30 degrees in magnitude. Then the theta here would be plus 30. With this position of the rotating line, the angle that you would associate would be plus 30. Angle measured with respect to the positive direction, going in the anti-clockwise sense, would always be referred to as a positive number. Whereas, suppose this be the position of the rotating line and you choose to measure the angle theta this way. You choose to measure the angle theta this way. And suppose the magnitude of this angle is 30 degrees. Then along with the sign, this angle would actually be referred to as minus 30 degrees. This would be a negative angle. However, there are very many angles that would describe the same position of the rotating line. The same position of the rotating line could be described by many angles. For example, look at this position of the rotating line. Look at this position of the rotating line. Now, one way to describe the angle that it makes with the positive direction of the x-axis, suppose this angle is 30 degrees in magnitude. Suppose this angle is 30 degrees in magnitude. So, one way to describe the position of this rotating line is by saying, well, theta equal to minus 30 degrees, which means that if you go an angle of 30 degrees in the clockwise sense with respect to the positive direction of the x-axis, then you can locate the rotating line. That's one way. The other way to measure the same position of the rotating line is, well, you could have said, to arrive at this position of the rotating line, I go anti-clockwise like this. I go anti-clockwise like this. But realize that this angle, if this is 30 degrees in magnitude, then this angle would be 350 degrees. And the manner in which the OP is arrived at, if you rotate this way, if you go this way, that is anti-clockwise, is positive, because this angle then would be referred to as 330 degrees. That means both theta equal to minus 30 degrees and theta equal to 330 degrees are ways of describing, equivalent ways of describing the same position of the rotating line. Or you could even have said, well, not just 330 degrees, you could have gone 330 degrees plus another 360 degrees, right? A 330 degree plus another 360 degrees. That's another way to locate the same position of the rotating line. Or 330 degrees plus 360 and another 360. That's yet another way of describing the same position of the rotating line. So, the same position of the rotating line can be described in many ways. Now, having understood this idea, I hope all of you are clear with this, right? Now, think of a rotating line of length r. OP is the length. OP is the length. So, OP would always be a positive number. While this rotating line of a given length r rotates, the point P, the tip of the rotating line, would have different coordinates x, y. This point P, the tip of the rotating line, this point P, the tip of the rotating line, x, y, while it rotates, would have coordinates that will depend on the angle theta. For different thetas in general, you have different pairs of x and y available for the tip P of the rotating line. Now, suppose the rotating line has rotated an angle theta. In the process, the tip of the rotating line assumes coordinates x, y. We then end up redefining our trigonometric ratios away from the right-angled description of trigonometric ratios is as follows. We then define sine theta, for example, as the y coordinate of the tip, which could be positive or it could be negative, Sine theta is described as y, the y coordinate of the tip of the rotating line divided by the length r of the rotating line. That's sine theta. We define cos theta. As the x coordinate of the tip divided by r, and we define tan theta as the y coordinate of the tip divided by x. That's how trigonometric ratios are defined, based on the coordinates of the tip of a given rotating line of a known length r. X and y are algebraic. Based on where the point P lies, x and y would have their own signs. Now, all of you understand that the xy plane is categorized into 4 quadrants. This is referred to as the first quadrant. This is referred to as the second quadrant. Now, in the first quadrant, realize that both x and y are positive. In the first quadrant, x and y are both positive numbers. The x and the y coordinates of any point in the first quadrant would be positive. In the second quadrant, x is less than 0 and y is greater than 0. For any point P lying in the second quadrant, the x coordinate would be negative, whereas the y coordinate would be positive. The third quadrant, for any point P in the third quadrant, the x coordinate would be negative and so will the y coordinate be. The fourth quadrant, this is the fourth quadrant. In the fourth quadrant, X would be positive and Y would be negative for any. So these are the four quarters in which we define all points in the xy plane in a given plane. So a given plane in general is fragmented into four quarters: the first quadrant, the second quadrant, the third quadrant and the fourth quadrant. In the first quadrant, like you understand, x and y are positive. In the second quadrant, x is negative whereas y is positive. In the third quadrant, x is negative, y is also negative. In the fourth quadrant, x positive whereas y negative. And this is how trigonometric ratios are defined in general, which has nothing to do with a right angle triangle really. And if I define my trigonometric ratios in this manner, then theta could have any value. It could be acute, it could be obtuse, it could be any number as you want. So this is very generalized. This is very generalized and has no bearing on the existence of a right angle triangle. So from now on, you're not going to look at trigonometric ratios from the perspective of a right angle triangle or an acute angle. Theta can be acute, obtuse or of any value. Depending on the coordinates of the point P, the trigonometric ratios of the corresponding angle theta could be defined as follows. And of course, cosec theta would be 1 by sine theta, sec theta would be 1 by cos theta, and cot theta would be 1 by tan theta, etc. Now, the important thing, and which would be very evident, very obvious, is the following. This position of the rotating line could have been arrived at in very many ways. A certain position of the rotating line could have been arrived in very many ways. That means the tip P could assume this position. The tip P could have assumed this position. That is, could have had coordinates x, y, could have had coordinates x, y if the rotating line rotated an angle theta, or it rotated an angle 360 degrees plus theta, or it rotated an angle 360 degrees into 2 plus theta, and so on and so forth, right? You could rotate 360 degrees from this position. This is the reference line, by the way. This is theta equal to 0 degrees. Theta is 0 degrees. This is theta is 0 degrees, right? You could have gone theta, you could have rotated theta and arrived at coordinates x, y. Or you could have rotated theta plus 360 degrees and you could have still arrived at coordinates x, y. You could have rotated 360 degrees into 2 plus theta and could have yet arrived at the same coordinates x, y of the tip of the rotating line. And it's just the tip of the rotating line which is instrumental in defining the corresponding trigonometric ratios. Which means now, can I not say the following? If sine theta is y by r, we can also say, well, sine of 360 degrees plus theta, right? That means if the rotating line has rotated 360 degrees plus theta, the rotating line has rotated 360 degrees plus theta, the tip would still arrive at this point x, y, and if the tip still arrives at the same point x, y, then the corresponding trigonometric ratio would still be the same. That means, again, same with cos theta. So cos of 360 degrees plus theta is cos theta, and tan of 360 degrees plus theta would be tan theta. So the trigonometric ratios will depend only on the final position of the rotating line. The trigonometric ratios will depend only on the final position of the rotating line. Whether you rotate theta or you arrive at this position, same position of the rotating line by rotating this angle. This angle is how much? If this angle is theta, this angle is how much? This was 360 minus theta. But if this is 360 minus theta in magnitude, this is 360 degrees minus theta in magnitude. If you take it along with its sign, realize that you are going in which sense? You are moving in the clockwise sense. In the clockwise sense, this angle would be referred to as minus of 360 degrees minus theta. Minus of 360 degrees minus theta. Which means the value of a trigonometric ratio for theta would be the same as the value of the trigonometric ratio for minus 360 minus theta. That means if sine of theta is something, then sine of minus 360 minus theta would also be the same thing. Why? Because both these rotations lead to the same position of the rotating line, and therefore the same coordinates x comma y of the tip of the rotating line, leading to description of trigonometric ratios as y by r, x by r, y by x as described. So it does not matter how much the rotating line has rotated, as long as you arrive at the same final position of the rotating line, it will bear the same value of the trigonometric ratios. So the things that we've learned so far in this: number one, the positive direction of the x-axis. The positive direction of the x-axis is the reference for measurement of angles. After all, when you measure angles, you need to have a reference line. So the positive direction of the x-axis is the reference line for measurement of angles. So this is referred to as theta equal to 0 degrees. Any departure from the positive direction of the x-axis, in the anti-clockwise sense, would lead to positive description of angles. Any departure of a rotating line referred to the positive direction of the x-axis in the clockwise sense would lead to negative description of angles. Angles described then would be referred to as negative angles. So this is a key thing, number one. Number two, the value of the trigonometric ratios will be defined only in terms of the coordinates x comma y of the tip and the length of the rotating line under consideration. And that is how those trigonometric ratios are defined. So whether you are rotating 120 degrees or you are rotating 120 degrees plus 360 degrees or 120 degrees plus 720 degrees, as long as you are arriving at the same final position of the rotating line, you would get the same value of the trigonometric ratio. That means sine of 120 degrees would be the same as sine of 120 degrees plus 360 degrees, would be the same as sine of 120 degrees plus 720 degrees, and so on and so forth. You'll have the same value of the trigonometric ratio. And not just that, I also said that suppose the rotating line has rotated 120 degrees. This is 120 degrees. That means you could have arrived at this position of the rotating line by describing 120 degrees in the anti-clockwise sense. This is anti-clockwise sense. Now if this is 120 degrees, this angle in magnitude is 240 degrees. This angle in magnitude is 240 degrees. But in order to arrive at this position of the rotating line, in moving in a clockwise sense, then the algebraic angle described would be minus 240 degrees. That means the trigonometric ratio for 120 degrees would be the same as the trigonometric ratios for minus 240 degrees, or would be the same as the trigonometric ratio for 120 plus 360 degrees or 120 plus 720 degrees, and so on and so forth. So it does not matter. You'll have the same, I repeat, you'll have the same value of the trigonometric ratio as long as you are able to arrive at the same final position of the rotating line, and therefore the same pair of coordinates of the tip of the rotating line. Is that clear? Right? Now, once you understand this, let me arrive at few more results related to this. Suppose this is a rotating line OP and this angle is theta. This angle is theta. Suppose the coordinates of P at this position of the rotating line are x0, y0. x0, y0 are the coordinates of the tip of the rotating line. And let's say this length is r. This length is r. Now, let's say another position of the rotating line. Another position of the rotating line, let's say OP prime. And this position arrived at by moving in a clockwise sense. By moving in a clockwise sense, the same angle theta. So then this angle would be referred to as minus theta. If this angle in an anti-clockwise sense is referred to as theta, then this angle in a clockwise sense would be referred to as minus theta. This angle would be referred to as minus theta. Alright. Now, given this, and this length again is the same as this length because we are talking of the same rotating line with its one end fixed at O and the other end swiveling in the xy plane. Alright. If the coordinates of P are x0, y0, that means this length is x0. Then what's the x coordinate of P prime? See, if the x coordinate of P is x0, then the x coordinate of P prime would also be x0. This one. Now, the y coordinate, this length, realize, is equal to this length. Why? Because this triangle is congruent to this triangle. This triangle is congruent to this triangle. So, if the y coordinate of P is y0, then the y coordinate of P prime would be minus y0. Y coordinate of P prime would be minus y0. Y coordinate of P prime would be minus y0. So then, let's start connecting the trigonometric ratios for theta and the trigonometric ratios for minus theta. What is sine theta? When you talk of sine theta, you're talking of this position of the rotating line. You're talking of this position of the rotating line, and therefore you are referring to the coordinates of this point P, that is x0, y0, x0, y0. Sine theta is defined as the y coordinate of the tip divided by r. Y coordinate of the tip divided by r, where r is a positive number always because that refers to the length of the rotating line. Sine theta is like a y0 divided by r. Sine theta is like a y0 divided by r. Now, when I speak of sine of minus theta, that means sine of this angle, then I would have to look at the coordinates of this tip, P prime, coordinates of this tip. What's the y coordinate of P prime? The y coordinate of P prime is minus y0. That means sine minus theta is going to be minus y0 divided by, sine of minus theta would be minus y0, y coordinate of this tip divided by r, that's sine of minus theta. What does it lead to? As you can see, sine of minus theta becoming the same as sine theta. Sine of minus theta becoming the same as sine theta. So that's an important result. Sorry, sine minus theta being minus sine theta. I'm so sorry. Sine minus theta is minus sine theta. Sine of minus theta being minus sine theta. That's an important result. Sine minus theta is minus sine theta. Now, what about cos theta? When you talk of cos theta, you'll talk of this position of the rotating line, and therefore it's going to be x0 divided by r. x0 divided by r. What about cos of minus theta? Cos of minus theta again would be the x coordinate of the point P prime, which is x0, same as P, right? x0 divided by r, leading to cos minus theta being equal to cos theta. Cos minus theta being equal to cos theta. That's another important result. cos minus theta being equal to cos theta. And then look at tan theta. Look at tan theta. Tan theta is what? Tan theta is y naught divided by x naught. Y naught divided by x naught. Tan theta is the y coordinate of the tip divided by the x coordinate of the tip. Y coordinate of the tip here is y naught divided by the x coordinate of the tip, that's x naught. That's tan theta. And what about tan minus theta? Tan minus theta would be the y coordinate of the tip, which is minus y naught, divided by the x coordinate of the tip, that is x naught. X naught. What does it lead to? It leads to, realize that tan minus theta turns out to be minus tan theta, because these two numbers are negative of each other, So then tan minus theta is minus tan theta is minus tan theta. Tan minus theta is minus tan theta. Now, these are some important results in what we refer to as associate angles, trigonometric associate angles. And let me also bring you face to face with the new unit of angle. So far, they've mentioned degrees as the only way to measure an angle theta. From now on, we look at a bigger unit of measurement of an angle theta. The bigger unit of measurement of an angle theta is referred to as a radian. The different unit that we are looking at now is radian. So by and large, we would look at the angle not always in degrees, but also in radians, the new unit of measurement of an angle. The new unit of measurement of an angle is radians. We look at, see, what you have learned so far is degrees, that's your old measurement of angle, and then the new unit of measurement of angle is going to be what we refer to as a radian. Radians. This is the new unit of measurement of angles. So then, how do we migrate from degrees to radians and vice versa? What's the conversion? What's the conversion for migration from degrees to radians? The migration is provided by the following. We define pi radians, where pi, you know, is approximately 22 by 7. Pi, you know, is approximately 22 by 7 or close to 3.14 Pi radians is 180 degrees. Pi radians is 180 degrees. That means 1 radian would be 180 by pi degrees. 1 radian would be 180 by pi degrees. And conversely, if 180 degrees is pi radians, if 180 degrees is pi radians, if 180 degrees is pi radians, then 1 degree would be pi by 180 radians. 1 degree would be pi by 180 radians. That's 1 degree. 1 degree is pi by 180 radians. That means, let's say 30 degrees. 30 degrees would be pi by 180 into 30 radians. That is pi by 6 radians. 30 degrees would be pi by 6 radians. 45 degrees would be pi by 180 into 45 radians, that is pi by 4 radians. That is pi by 4 radians. 60 degrees would be pi by 180 into 60 radians. That is pi by 3 radians. Similarly, 90 degrees would be pi by 180 into 90 radians. That is pi by 2 radians. And so on and so forth. And so on and so forth. The conversion is this. 1 degree, each degree is pi by 180 radians. Each degree is like a pi by 180 radians. Using this, you can convert any angle in degrees to the corresponding angle in radians. So, suppose theta is known in degrees. If theta is known in degrees, then each degree would be pi by 180 radians. Each degree would be pi by 180 radians. So, theta degrees would be these many radians. If we have theta in degrees, then the corresponding angle in radians is going to be pi by 180 into theta. This would be the angle in radians. If you have theta degrees given to you, you want to find how many radians are contained in theta degrees, then the radians contained in theta degrees would be pi by 180 into theta. These many radians would be contained in theta degrees. So that's the migration from radians to degrees or degrees to radians. So given a certain angle in degrees, you want to find the equivalent angle in radians, then all that you need to do is multiply by pi by 180. Pi by 180 would give you the conversion from degrees to radians,